All right. Well, this is and Adam, I like your title for this. Because I was like, because I wonder, like, is it a ZFS data corruption bug old enough to vote? I mean, that's very, that's
very wordy,
very, very wordy. And then you got like, you kind of want to play into adulthood because it is 18 years old. But I just love it. It's all grown up. Our little baby data corruption bug is all grown up and it's gone into the world.
And definitely no question about whether we try it as an adult.
No question whether we tried it as an adult. I mean, like, look, we probably would have. I mean, if this had been a 16-year-old ZFS data corruption bug, we probably would have tried it as an adult. Don't you think?
Exactly.
But yes.
Yeah, for sure.
But now we don't even have to have the conversation. Now it's like this.
Precisely.
This bug is going away for the rest of its life. So, that's let's not go too far with that analogy. As with many analogies, I wish I had stopped several elaborations ago.
Sounds right.
Okay, so because the great thing about this bug is it includes a bonus data corruption bug that we debugged in trying to debug this one. So, Alan is here. Alan, this one starts. Tell us how this one starts, because I think this one starts with you noticing that we had our pod. Just ring the chime early. We had our podcast episode on Crucible, which may have been as recently as a month ago, as long ago as 5 years ago. I really don't know.
Somewhere in that range.
Somewhere in that range.
I would just note on that Crucible one, I think I think Alan and James were a little bit reluctant to come on the show. And I think it was like, look, don't worry, nobody's going to listen to it anyway. It's fine. And it was, for a long time, our most listened to show. So sorry that we misled you on that one.
Even if you take
it was a minute ago.
Listens out. If you
if we take your mom did like re-listen to it quite a bit. She was clearly looking for something. So if we take
not finding it, yes.
Yeah, just not finding it exactly.
Yeah.
No, it was a popular one. No, I think Adam, the reason to not want to talk about it is the reason you never want to talk about a system that's responsible for data correctness.
Integrity.
Data integrity, because you don't want to taunt the gods. You don't want the listener that you are worried about on that podcast is the gods. The gods tuning in and being like, oh, that's a pretty fancy system you got there. It sounds like you're pretty proud of it. That sounds like it always gets the data correct. Well, maybe it doesn't, pal. So that is the reason that I think we're all very superstitious about talking about this stuff. And hey, we shot our mouth off, and here we are. Alan, I'm sorry. Clearly, this data corruption bug is a direct responsibility of us convincing you to be on the podcast. So we're really sorry for that. But so how does this thing start? Because you noticed that we had got some data corruption on Crucible volumes in our dog food rack. Is that correct?
Yeah, I think Angela might have actually flagged the issue first, and then I went and looked and said, yeah, we are failing to decrypt a block, which was very puzzling to all of us, because we're like, that, how, what, a lot of confusion. And yeah, I mean, you can sort of read the beginning of the issue, but certainly there's a lot of confusion going on.
And what are the kind of the initial? So we always encrypt by default.
Yeah.
So a failure to decrypt is alarming, because that can indicate data corruption.
Yeah, and we hadn't seen like this particular panic trip in, I don't know, 3.5 years or something. And since we were still developing the code. So it was very confusing, and like, how could we get here? What's going on? I think it took a day or so before we really analyzed the problem and figured out that we had this, on this one extent, we had 32K that was all zeros.
I do like this issue, which we've linked, is itself literature, and I do love the line, casting around in desperation, I find some detritus, which feels like, I mean, that just feels like a one-line poem of for debugging data corruption. So yeah, so what do you find in the detritus?
I'd have to. I need to bring up the issue too, so I can reference my actual statement.
I mean,
and while you do that, Alan, I would just quick aside, and I hate to be the senator from context, but
I would like to advise you that you're under oath. Is that where you're going with this?
That's right. No, I was going to say we are talking about the Oxide storage service,
Yes.
which provides virtual disks to virtual machines. We talked about it a bunch on that episode, but just for a teeny bit of context, it has ZFSs, some underpinnings. We store data in triplicate on 3 different distinct servers, and then provide a redundant, virtual disk to these virtual machines.
That's right. And we had actually, Alan, you had said we had not seen this since we were developing Crucible.
Yeah.
But in fact, a very important change had been made to the surrounding system. In that, and cue episode, much more recent episode, we had Dave had done and team had done this terrific work on update, and we were now updating a system while it was more in motion. We were not parking the rack any longer to update the system, which meant there was going to be more rebooting of sleds while there was effectively activity.
Yeah, I think this is definitely a key part of what the eventual issue is, that we had done a lot of testing of restarting processes and verifying things that way, but we hadn't done a lot of like power off the system, power it back on testing. And I think that was sort of a new area for us.
But that is probably not top of mind when you're seeing data corruption. Or maybe it was, I don't know. And as you were casting about in desperation, finding detritus.
Well, I think, in the beginning, there's a lot of desperation. There's a lot of casting around. Part of the issue is that we're doing a lot of things here, and it's not clear which one is the one that makes a difference.
Right.
So we're like, here's some things that, there's lots of things that changed. One of them was the update. We pretty sure it wasn't update related directly, but still not sure.
Right.
There's always a lack of confidence in the code you wrote when, that's the first place you go to, because it's got to be me.
It's got
to be me.
Right.
So you always, suspect your own stuff. And then there was some, we weren't sure if the live repair was part of the problem. I think one of our challenges here was that we didn't know that there was data corruption until we tried to actually read the block.
Okay.
So something happened at some point in the past, and now down the road, we try to read the block, and then there's a problem.
Yeah. Yeah.
So initially we were like, well, something has happened at some point, and we've got this corruption, but we don't know what the timeline is. We don't know the start date yet.
And which is the insidious factor of data corruption. Data corruption both at rest and even in memory, because you're separated at such a distance from discovery from when the thing occurred. And obviously, data at rest corruption is much worse. But in all cases, you're like, all I know is I found it here. There's, the way where it was introduced, who knows?
Yeah.
Yeah, and it was introduced sometime in the distant past, and you often have, at first, little data other than the corruption itself. And the corruption itself can be important. And what are we able to determine about the kind of the contour of the corruption, if anything?
Well, we know that it's 32K of zeros, and it's right at the start of the file.
Okay.
And so far, it took us a little bit to find that initially. And then once we had that sort of data point, we were able to sort of build a verify tool. Matt, came up with a plan, and so we could go and then verify. And we went and verified every single downstairs that we had on dog food to see if this was anywhere else.
Okay, and what did we find?
So on the first time we looked, we only found the one failure case.
Okay. And so, whether is that of relief or not? That's kind of like, it is what it is. So
it is. Yeah. It's good because you don't want to find it, but then if there's a problem, you want to find it, and you want to find it as, I don't know.
Yeah. Yeah, if it was happening everywhere, in some ways, like obviously that's much worse.
Yes.
But it also means
but
like it's probably going to be
right.
findable.
Right.
Yeah.
That's right.
Right. It's like if I have one ant, it's like, am I going to follow it everywhere? If I have a billion ants, it's like I probably can find where they're going.
Oh, that's interesting. I'm going to try that next when the ants come back here in the wet season. I'm gonna remind Bridget, like, hey, at least we have a million ants.
Our glass is 1,000% full. Okay.
Can you imagine
Adam
how difficult this would be if there were just a single ant? I'm gonna try that. Oh, I like that one.
I'll work on that metaphor.
Yeah, that's right.
Yeah. So this, and unfortunately, this also gave us other escape routes that maybe we'll get to later. But only having one case of this, that sort of gave us the option of like, well, what if something else outside of Crucible corrupted the
Right.
file by accident?
Right.
So we sort of that was sort of like a escape hatch we had in the back of our mind. But I don't want to get too far ahead.
Yeah. And is that that just also is a kind of a grip of terror too, because something outside of Crucible is corrupting, and it's like, I mean, even worse. I mean, really
Worse.
worse
And
for us, maybe better.
Worse
Worse
for
for
us.
somebody else.
Exactly. That's
Yeah.
right.
Well, if there was like if we were running some program that was like trying to find problems, then I don't know. It was desperation.
Desperation. Okay, so we find it in one. This is the only spot, basically. The place we found it. And again, it is what it is. Some solace, but we found it in the one spot.
Mm-hmm. And I think I found the desperation quote, and that was actually part of the challenge here was that we were doing all these rebooting of sleds, which was we weren't able to get the logs on the sled right before the reboot, so we'd sort of lose some of our history.
Right.
So we didn't know. We knew, well, here are some of the things that happened, but there's some stuff that's in this sort of behind the moon, the dark side of the moon. We don't know what goes on there. And Dave went in and added some additional stuff that would help us sort of pick up the logs after a sled had been rebooted, in a surprise manner that later on would help us.
Oh, interesting. Okay.
One of the other things we did at this point is started stuffing more data into spare bytes in the Crucible extent files, where we had like 48 byte slots for the encryption contexts, and we were using like 42 bytes of those for actual data. And so we just stuck other information in the remaining 6 bytes so that we could then look at that after the system came back up. And so in this case, it was like the specific flush number that had last been seen by the system.
Yeah, interesting. And I feel we've talked about this a lot on our most vexing bugs, but I think this is an extremely important technique that you're talking about, Matt. This is a half measure. This is not fixing the bug, obviously. In fact, this is presuming the existence of the bug, which is a very reasonable assumption, and then asking yourself the question, what additional information would we like to have when we next see this? And I actually think that this is, not only is this very technically important because it assures that you will get more information, I actually think that this is very psychologically important because now you're rooting for the bug to occur again, which of course you always are rooting for the bug, but you're also like, I don't know, maybe this is my own psychological terror that I'm gripped by, but it's like
it gives you something to do too. Like you're taking action,
Taking
having
action.
some
No, it's
agency
important.
in
I do think it's really important having some agency. Right. Exactly. Like the bug is no longer doing this to you. You are doing it to the bug, which is very important. So so we add, and so Matt, you're describing, so that was the actual, so describe the flush number a little bit and why that was something that we actually wanted to have in there.
Yeah, so the way that Crucible works is it's block oriented, and each block has both the like raw data that's being stored, which is encrypted, and then some amount of encryption metadata, which is like the nonce and things that we need to verify that the encryption decrypted successfully. And those are stored in 2 separate places. And so we have a particular little dance that we use to make sure that there is always at least one set of valid encryption metadata for every block. So in this case, we have 2 what we call slots. We write encryption metadata to one slot, then write the block data. And that way, if we lose power halfway through this, the encryption metadata from the other slot is still valid and we can decrypt the block. This is all like, in theory, there was actually a bug related to this that we found while debugging this other issue. but those slots are just a fixed location on disk, and we weren't using all of it. And so the flush number is whenever we flush the system, whenever the VM sends a flush, we increment the flush number internally, and then we write that to each extent file. And so having the flush number gives us some idea of ordering in the system, where we can see like, okay, this was flushed, or this block was flushed at a particular flush number, and this block was written at a particular different flush number, so we know the order in which they landed on disk.
Right. So we get that absolute ordering, which is potentially hugely important, or it would be a very important additional piece of data about this problem. And then, Matt, when is it in here that we discover the bonus data corruption bug?
So the bonus data corruption bug, I think, was mostly thanks to Justin, who set up a little Jepsen cluster with Crucible and like wrote a hacky adapter to be able to run Crucible with the Jepsen style of like randomly killing the network and randomly restarting systems. And he started noticing different looking data corruption and different looking failures to decrypt in his system, which was obviously another bad sign, but it was different shapes. So it was not like the first 32K of data being zeros. It was that like specific blocks or specific contexts were failing to decrypt, but like scattered randomly through the file instead of always at the beginning.
And then, so then now we have got the bug that we've got, because in that bug, we've got a decent amount of reproducibility on. And so we've actually got that one maybe in a position to be able to debug.
Yeah, and so that one, I was actually out at the factory, theoretically working at the factory, but in practice just working on data corruption because the factory was in good shape. And that ended up being us misusing or relying on Crucible's ordering guarantees, or relying on ZFS's ordering guarantees in a way that was not quite correct. So there's a specific ticket. Let's see if I can find the specific link to this.
Matt, is now a good time to bring up what Matt Ahrens we have taken internally to calling the affidavit? Matt Ahrens, do you know that we call this the affidavit? Is this like, because this is such an expression that we use, I would say frequently, but we may not have.
No, I haven't heard that.
Okay, well, you were the one who signed the affidavit, so I think maybe it's important for you to be aware of the affidavit.
Uh-oh.
Yeah, no. I mean,
just because we have it printed on the wall.
Exactly.
Look, you guys are going to make him start bringing a lawyer to every one of our text message conversations, okay?
No, in fact, I don't want him to bring a lawyer. That is actually, you don't need to bring a lawyer in here. We don't need, the lawyer's just going to slow everything down.
When you say that, it makes it sound like I need a lawyer.
That's right.
Oh, no.
As it turns out, I was the one that needed the lawyer here, so you're fine. But so the affidavit was way back in the past. Crucible stored its encryption metadata in SQLite, which was like very guaranteed to land on disk and very guaranteed to have strong ordering and everything, but also was flushing to disk like all the time because that's what it does. And so we switched a couple years ago to what we called a raw file format, where the encryption data and the block data were stored in the same file. And this is where I was talking about how we write one set of encryption data, then the block data, and if we lose power in a situation with things are half written, the stuff is still allowed to decrypt. And I think Adam went to you, Matt, and asked, like, what guarantees do we have about the actual order in which ZFS writes land on disk? And you wrote a very thoughtful write-up about this, explaining that things would mostly land on the disk in order with a few subtle exceptions. And we took that as gospel. And it turns out that we were violating one of those subtle exceptions in this second bug that we found while investigating the first bug.
Okay, so I was 1 for 2 in my affidavit.
No.
I think the affidavit was correct.
No, the affidavit is correct.
Yep.
We misimplemented very subtly the affidavit, the terms of the affidavit.
And so
okay, but the bug that the ZFS bug that you guys found seems like
that one like,
that's wrong, right? Like that is not adhering to the affidavit.
That is correct.
Okay.
But as your lawyer, Matt, I would just say in OpenZFS at the time of writing the affidavit, it may have already been corrected. So we'll just submit that to the jury. But please continue, Matt.
Yeah, so the ordering issue was that ZFS writes will land on disk in order unless you have written the same region more than once. because when ZFS goes to persist writes to the ZIL, it looks at the current state of data. So if you imagine writing offset 0 to a certain value and then writing offset 0 to another value later on, when it's persisting, it will get the later data when it persists the first write to the disk. This is all very hard to explain while just like gesturing wildly at my computer.
I think we got you. We can hear your gesturing. Your gesticulating is coming through in the audio. So I think that's what is pointing out in the chat. Like, isn't affidavits don't really have terms? They're sworn statements. And yes, this is a sworn statement from Matt about the way ZFS works. And so that's exactly what this is.
I think that it's maybe confusing for folks because you would think that like when you do operations, they either get logged or they don't get logged. Like I'm doing some writes and like hopefully you're logging them, right? Like you do a write command and then it gets logged and then you do another write command and then that gets logged later, right? But the delayed logging in ZFS allows for improved performance in a lot of cases, but also can introduce these strange behaviors like where you're saying, you do a write and then you do a later write and then the logging pulls in the later data instead of the earlier data. It's all because of this delayed logging, the potential for delayed logging in ZFS, which I think is kind of maybe the root of all evil at least in the ZIL.
Well, I mean, performance is the root of all evil. So by extension, this is very close to the root of all evil. But the need to make highly performing systems. Or correct systems, because as Alan is fond of pointing out, it's like if we can eliminate the correctness constraint, I can make this thing really, really fast. So between the two of them, there are two gnarly constraints in terms of correctness and performance. Okay, so Matt, we find a bonus bug, and we're
able to reproduce it.
We're able to reproduce it.
The Racklet, so where it's like, okay, yeah. And Matt has an idea on where this is. Let's add this extra sync in at this particular step.
And as I recall, was the fix to that like actually fewer syncs? Am I remembering that correctly, Matt? Or
no, it was more F syncs. It was more F syncs. We basically had to add an F sync. Yeah, of course. The cause of it's either fewer or more F syncs will fix everything. So we fixed this bug, but I think I remember at the time telling people like, I do not understand how this bug could cause 32K of zeros to show up at the beginning of the file. So like I was still waiting for the other shoe to drop at this point because I was like, my mental model of the bug perfectly predicts the behavior that we've seen on the Jepsen test and everything, but it really does not predict this data corruption.
Which does have a very specific signature in terms of the 32K being zeros. And maybe actually at some point, maybe now is the time, Matt Ahrens, to, because it reminds me a lot of the, if memory serves, the last 64 bytes being corrupted due to is it the Silicon Image controller? Am I remembering that correctly, Matt? Do you remember this?
No.
Oh, you are really? Am I okay? Now I'm worried that this is dementia, because this is the data corruption bug that you and Bonwick had early, and you're like the last 64 bytes of a block I think was stale, if I remember correctly, and
what? I mean, we're going back like more than 18 years.
More than 18 years. No. This is definitely more than 18 years. This is way more than 18 years. This is definitely in the 20 plus category. And this is early enough in ZFS that you and Jeff are like, this is a ZFS data corruption bug. Like we've got data corruption somewhere in ZFS. This was at the time when people are starting to run it on their desktops and so on. So it's like people are running it kind of experimentally. But you two believe that this has got to be a bug in ZFS, and you're going back over and over and over and over ZFS and not actually finding anything. And then I can't. God, I was really hoping you would remember, because now someone observed that this was only happening on a particular DMA controller, but it's like and again, I think it's Silicon Image, and maybe am I one, do I have that correct? Two, am I mispronouncing it? Because now I'm like, is that supposed to be Silicon Image?
I think it's Silicon Image.
It's Silicon Image. So why am I giving it like? Why am I making it
this.
fancier with Image? What am I doing over here? Am I just? But as we know, I mispronounce many things, including the word image. Apparently, although I do know the word image, I'd like to say that. I just thought that they were. I don't know. Is any of this coming? Is this? Are we still like still waters on this one? Is there anything that is rippling?
Yeah, I don't remember this at all. That was like. I was probably like 23 years old or something. And,
yes.
I'm like twice that old now. So,
Adam, I know that you may
You're
not
talking about childhood memories. Like this is Matt's first memory.
I know this.
Yeah, pretty much. Pretty much. Well, but also probably there were probably a lot of bugs in the first like year or two of ZFS, and this is one that rose to the level of like people outside of the ZFS team noticing it or like hearing the story. But it's probably lost in the tsunami of early bugs in my mind.
It's much easier now. We're dipping into the realm of trauma. Like Matt has erased this memory from his.
I know. I at some point I'm gonna. But Adam, do you remember this? Am I? I am now.
I can say with certainty you're making this up. You're making this up for attention or for content. But nobody else remembers this.
I think we don't know why you're making it up exactly. The only thing we can say for certain is that this is completely fabricated. No, so this DMA controller had it was always on the same DMA controller, but it was like, no, that's impossible because this DMA controller is like this is a very popular DMA controller. And there were literally millions of them in the field. And ultimately, it was found when the DMA satisfied certain VA constraints, it would simply not write the last 64 bytes. And it was wholly on the actual the controller or on the HBA. And this was, and I just remember, apparently I'm the only one that remembers this, or I implanted this in my own memory as something that was convenient, just because there was this moment, Matt, where certainly I had the realization of like, there is rampant data corruption in the world that only ZFS is detecting. And it was just a real eye opener about, but again, this story is definitely having less resonance because I'm the only one. The fact that it's completely fabricated may make this slightly less impactful, unfortunately.
But not completely. I mean,
yeah. Thanks for. Meanwhile, Adam's like, don't jump in there and save him. Let him drown. He needs it.
Well, just to throw a small life preserver, I would say that Matt and I definitely came to the same conclusion about data corruption being everywhere when we were at Delphix, where we were running ZFS on top of EMC arrays, and they would upgrade the EMC array, and we would detect all this data corruption, and customers would come back and say, "Well, none of our Windows boxes, even noticed." Like, yes, you're welcome.
Exactly, that's right. Right, exactly. Well, so the moral of that story / fabrication was that the particular pattern of corruption, it doesn't really matter, and the fact that we had this first 32K being zeros was a very specific fingerprint. Matt, as you say, the bonus data corruption bug did not match that fingerprint, and it just felt, but the second one was still out there.
Well, this was actually when I told my wife, it was still in the first one. Like we didn't know. Everything was on the table in the beginning. Like, it's us. Is it us? Where is it? So, but finding the first one that Matt found, I was trying really hard to convince myself this could be it, or there could be some other rogue agent that had done something to do this 32K. Like, I don't know, but maybe squint really hard.
But so we are. I mean, we fixed that bug, Matt. You get the fix in for that, which is great, and we continue to test get back to test in this release.
Yeah, and now that we sort of had this scanner that Matt had made for us, I was going out and scanning dog food. Like every other day, I was scanning it, and because we didn't really have it completely polished. It took a couple hours to go dig through all the logs and make sure that, that's just a false positive because we're doing IO to the volume and things like that. So like we had sort of I was gathering data to look for this corruption while we were still doing updates in the background.
Yeah. Okay.
And dog food, it should be said, is the instance of Oxide, the Oxide rack that we use internally, and we do our dog fooding, our eating our own dog food. That is to say, of the next release.
Yes, and if you are actually in the Oxide office, dog food actually lives in the Oxide office and kind of looks the part. It's got, don't look it's it's taken some licks. That it is definitely not production anything, but it's been invaluable for us to be able to. So we are continuing to do. I mean, in part because we really want to test this update functionality, which has the side effect of bouncing boxes when they're doing real work.
Mm-hmm.
All right. So what's the next? We've got bonus data corruption bug fixed, and all of us thinking that well, it didn't exactly match the fingerprints, but it was a data corruption bug. We actually knew we definitely found a data corruption bug, which is very important, and we were very grateful to have that fixed. So Matt, great going on that. Great going by Justin to actually take this Jepson-like approach to testing it. What was the next turn here?
So I think we had. We did the first update of dog food to the new bits, and we found a bunch of problems. And there was some panic for sure, but then we had sort of looked at all of where they were and said, well, okay, this was the old code running as we're updating to the new code, and
right.
It was the problems we're seeing on the old code. So it sort of made sense.
Right.
We could look at it and say, yeah, okay, that we do see a bunch of these zeros, but it's all the old code where the bug actually happened during the update process. And once things had got to the new code, it looked okay. And so this was I think Halloween weekend. And I was like, I'm going to continue to do my background scans, and I'm going to do 3 more updates to dog food.
Yeah.
So we had the first one to the new bits, bunch of problems. I did another one, no problems, another one, no problems, another one, no problems. So I was like, okay, I think we got it, because I've done a bunch of updates now, which was our sort of reproducer.
Right. Right.
And everything was looking okay. So I was like, all right, I think, we'll let this one go into the wild. And then Angela did another update, and we had another instance that then panicked with this 32K zeros problem. And I think I sent...
Throughout this whole process, we'd been posting DEF CON pictures of various DEF CON levels in our group chat. So I think this brought us back to DEF CON 0.
Yeah, and I think I was so sad at first that I only DM'd Matt directly. I didn't put it in the storage channel. So I was like, I think I found another one. And so we started messaging back and forth, and it was like, yeah, this does look bad. And then there was I had to go back to the product huddle that week and be like, that bug that we said we fixed and we had stopped the release for, and now we're on a go. It's not fixed.
We're back to which again, I mean, given the mismatch in fingerprint, there is some solace in this, because there is this little piece that didn't add up from the previous bug. It just did not. It was really hard to talk our way into that. What feels like an extremely distinctive fingerprint. This 32K of zeros just feels very unusual.
Yeah.
Yeah, Matt, how was it? What was your feeling? What was your feeling when we hit this again?
Concern, I think, was what I posted in all capital letters to Alan.
Concern in all. Right.
But also the feeling okay, sure. I was waiting for the shoe to drop.
Right. We were kind of waiting for it, and okay, so we still have it. We fixed a bug. We know we fixed a bug. We fixed an important bug. We've got total solace in that. It was not as it turns out, was not this bug. Was not the bug that caused us to go search for this. So now what? How many corrupt blocks do you have, Alan, at this point?
I don't know if it was just one or if I had multiple. I think there may have been multiple cases in this time where we had. Yeah, I think there was a couple that were bad.
Bolded concern in all caps.
Yes. Because we had a little more logging now, and I had been doing these regular scans, I knew that like on October 30th, everything was good. And on November 1st, we had a problem.
Right.
So I had like a time bound.
Yeah, that's actually really important. Yeah.
And so then from that and from the logging, the new logging stuff we had, and sort of knowing a little better what we're looking for, I was able to like walk all the way forward from the good time to the bad time. And then once I had the sort of end state, I then walked backwards with the like, here's the truth table at the end, here's the truth table at the beginning, and sort of figure out where we got a corruption. And a scary thing about this was that because this corruption was sort of hidden from Crucible, at one point Crucible had repaired, like we have a three-way mirror.
Right.
And we had one of the legs of the mirror that had the corruption and two that didn't. But the IO is still going on. We don't even know that there's corruption out there. And then at some point we say, oh, these three mirrors aren't in sync. Let me make them all the same again. And we copied the corruption from one of the mirrors to the other mirror.
Right.
So that was like, the infection is spreading.
Right. It was the opposite of repair.
The opposite of repair, yeah. So, but I was able to sort of walk backwards, figure out, okay, I'm pretty sure this problem happened during a power cycle of a specific downstairs when it was doing repair of one of the extent files.
Okay. So that's a really important development.
Yeah. So like to know, okay, here is the condition that we think caused it, because that enabled me to go over to our sort of.
So this is, just to repeat this is a power cycle while we are repairing.
Yeah.
And repairing is not, that's not it's not an abnormal mode of the system in that we expect there to be some repair whenever a sled disappears and reappears, there'll be some repair happening.
Yeah.
So, and we expect sleds to come and go, but it's also like not, in kind of the default operation, we kind of expect sleds to stay up.
Yeah.
And so this is a slightly unusual operation to be engaged in a repair, and then to have to lose power while doing the repair. We've got a more unusual situation, which might explain why we don't see it as much as we would otherwise. You could explain why you'd be able to do a bunch of updates and not see it.
Yeah, and I think it was the double, the double thing here that really was the trigger. We need to be in this either repair or reconciliation, and then lose power.
Okay, so that's an important detail. What do you do with this detail? Because now you head over to one of our racklets and, if I recall correctly, start pounding on it.
So we do stuff to make sure that the disks are all busy, so that we know that on a power loss, there's going to have to be some repair that goes on. And then I just tried to keep narrowing the operations that still would show the failure.
Right.
And it does feel good when you're able to do it frequently, because that really gives you hope that you're gonna get to the end.
Absolutely. Yeah. Well, and so then we, at some point here, you were able to reproduce this now on the racklets.
Yeah.
And you are able to reproduce it way more than once.
Yeah.
Which is great news.
Yeah.
You were looking a little down, but I thought it was great news.
Yeah.
Because this is, we now are beginning to get a coordinate around this thing. And I think the thing that was both most vexing and most encouraging is all of this corruption had this same 32K of zeros fingerprint.
Yep. Yep. That was really, that was the happy part of the dark part of, I guess. Yeah.
That was the happy part of the dark part. Also, it's just weird. It's just like 32K is just like not a number sloshing around in a lot of places.
Yeah,
You know what I mean?
we had some ideas. Matt had some great bad ideas about changing certain ZFS tunables to see if maybe this 32K was something that we could, we were looking for anything that was 32K.
Anything that would, I love that. It is a great bad idea because anything that I can do to like, can I turn a knob and just change the problem? That way, at least I know that like, okay, these things are related somehow.
Yeah.
And we can begin to, because on the one hand, we've got a cordon around it and that we can reproduce it. But on the other hand, it's like, it requires, this only happens when we actually hard power off a sled. So it's like, which is not exactly an easy failure mode to go debug. Because the system is, it's off.
And I think James, both James and Matt and myself, we were all, there were lots of sort of false trails that we had attempted that didn't lead to anything. And there's lots of stuff going on where you read through the bug and you can see like knowing the result, it's entertaining to go back and read it and be
Right.
like, well, that's never going to work.
Right.
Oh, that you should have went that way, but you didn't, and you sort of see all the directions we wandering around there in the dark.
Yeah, I always think that all those directions end up being important because one, they allow you to better understand the system. Okay, I'm going to go explore this aspect of the system. And then you come out with like more confidence, or in the case of Justin and kicking the snot out of one aspect of the system, you discover something else which actually becomes germane.
Yeah.
And or you do develop kind of the better tooling along the way.
Yeah, there were certainly improved tooling that we came out of this with, where we can better inspect the sort of metadata and Crucible and things like that we're definitely going to keep going forward,
So Matt is saying in the chat that ZFS immediate write size is 32K. So let's change that to 60. Why not? Change that to 16K. But Matt, that does not. A great bad idea, a truly great bad idea. A terrific hypothesis, but no.
I just found this by rip grepping through like the entire ZFS subdirectory for that number showing up anywhere.
That is the sign of desperation.
It's not a good sign.
Yeah, but I think it's a great idea, and importantly, like you can do the experiment, and you can then really disconfirm it. Like, okay, this is actually like we
100%. It is both a sign of desperation and a great idea because it's one of these like hypotheses that is really easy to
test
and explore. Yeah.
Easy to test, easy to invalidate. Like, okay, not that one. Back to rip grab. And okay, so within what is the next kind of the next sequence of events? Are we at that Friday yet?
I think we're at that Friday. Yeah.
Yeah, and because there's a moment when because I was talking with you and Josh in particular about the prospects of this actually being a Z, because our assumption has been this is a Crucible bug.
Yeah.
Just in general. And
we had Robert denies knowledge of this, but I had gone to him originally with my, here's what we need to do to make sure we're repairing extents on an unsafe shutdown. And we worked together and came up with the sort of step-by-step copy the file, fsync the file, fsync the directory, move the file, like this, 7 or 8 fsyncs around this whole repair process so that we could know where we are if interrupted at any point and recover from that if interrupted at any point. And I felt like we had come up with a good, solid solution. Adam, I went back and looked, and you had actually reviewed this code and gave it your blessing. So I was like,
no.
Yes.
Yeah, we have a signed statement from you saying I Adam Leventhal in perpetuity. Yeah,
it's a deep fake.
It is in this case.
This was pre-deep fake, so. So yeah, we're on the Friday now, and I'm like, doesn't seem, I really can't find anything with Crucible that's wrong, and it really kind of feels like this might be something in ZFS with the Zilog, but how? I didn't understand how. Like, we're not, there are other people who use ZFS, and like
there are other people who use ZFS. Yeah.
So I was like, I don't know, but I don't know what to look for. Like what can we do to try to figure out?
Yeah. And I think that I definitely remember there's a little bit of like, well, this can't possibly be a bug in ZFS. And I think it's like the fact that something has been used for a long time, even with a terrific track record, I think does not, it may make it unlikely. And you should never, it should never be one's assumption that this is, but it's like chip bugs. It's like these things do exist. Mm-hmm. And Matt Ahrens, I know you're like, it's like, yeah, these things definitely exist, by the way.
Yeah. And I would add that, like, for sure, ZFS is used by a lot of people in a lot of different ways, but it's probably not, those people are not pulling the power plug and then relying on, strict ordering of a very careful system, carefully designed, application that's using it. So there's probably not a lot of other people that are doing what you're doing. I mean, there were enough that it was found in OpenZFS, ZFS on Linux, and fixed a few years earlier, but still it existed there. It existed in ZFS for like 15 years. So.
Yeah, and I think that you just can never really. You have to be just very, very careful about appealing to the longevity of a thing. I mean, again, it's all the reason in the world to say this should not be our first assumption, but we should. We need to follow where the data sends us, and wherever that might be, even if it sends us much deeper into the system.
But I think next is the sort of breakthrough is. James and what he discovered for us.
Yeah, so James, why don't you describe your breakthrough, because this was very important.
Excuse me. We had known that it was a power off during this repair process that seemed to be the problem. So we were talking about it, and it seemed like if this was true, this was a problem. We should be able to reproduce this with a small program, not Crucible, not the whole control plane and everything set up. So I'd been working on something else, but had been doing a little bit of this type of testing in a VM, in a Propolis VM, just running a program and terminating the Propolis hypervisor to simulate this power off, and saw the issue with a very small program. So simulating the part of the repair where we take something that we had copied from a remote downstairs into our current directory, and then copying that over the extent, you terminate the Propolis server, and then that simulated or reproduced the problem. Nothing else required. So that certainly was a surprising result there. We originally thought it was something. From there, we thought it was something in the Rust standard library, but we then reproduced it again with just a very simple C program. At that point, basically everything was pointing to some sort of an issue with ZFS.
Yeah. So I want to get to that program in a second. But so James, when you were you surprised that you were able to reproduce this so easily in Rust? Because this is a huge lurch forward, because now we are not powering off sleds. Now we are bouncing VMs. We've got Crucible out of the picture, which is. Yeah. Really great from Alan. I mean,
my wife,
Don't worry.
Got my job.
Don't worry. I'm not sure about everyone else. I think I may be the only one at the company. We may get rid of everybody else, but that was huge to get Crucible out of the picture. But now we've got Rust very much in the picture, and there is a period of time where it's like, okay, maybe this is a very weird Rust standard library. So it's like, let's go into how complicated can it possibly be? The actual path that writes to and James, you describe it just a little bit. I know you linked to it in the chat, but kind of because there are a bunch of operations that are happening where we're renaming, we're moving, copying files, renaming files, and so on. Do you want to describe that just a little bit? Because I think that's really important here.
So the Rust program writes out a file. So this would simulate existing data in a downstairs. So it writes out an extent file. The second step would be create this .copy file, write a whole bunch of random data there, completely different, simulating a file that we had pulled via the repair API from a remote downstairs. And then the third step was to use standard FS copy to overwrite from the copy file to the extent file. The fourth step was an fsync. And then it would keep doing this over and over, ticking up, incrementing the extents that it was working on, very much like our repair operation would do.
And so this is great news, because now this thing is much smaller, but it's looking like Rust is very much, it has a possibility here. So Dan then realized, like, okay, I'm going to try to actually reproduce this in C. And I just kind of saw this go flying by in the chat. I don't know, for whatever reason, I'm like, I don't know, that feels like a long shot, but which it shouldn't, because Dan is then able to like pretty quickly reproduce this in a C program. And if we had not been able to reproduce it in C, that wouldn't have necessarily that wouldn't have necessarily been a hugely valuable data point. That would not have pointed the finger definitively at Rust. Mm-hmm. But the fact that we could reproduce it in C meant that, like, okay, there's now a whole bunch of software that's not in the loop here. Yep. That now we are really down to not very much in terms of like, this is very clearly now a ZFS bug. This is Crucible. Not only can Crucible go home, all of Rust can go home. Yeah. So this is this is good news. And then this is one of the advantages of having a global team is sometimes when it's time for some of the members of the team to go to bed, other members of the team are just getting up. So Andy, at some point you kind of come in here to, I think, your Monday morning, and having seen all this having gone on.
Yes, that's right. Came in Monday morning with my time zone advantage, and there was a lot of chat to catch up from over the weekend. But, nice place to be in. We've got a small C program that reproduces this, and James has proven that it reproduces. So I take that and I spin up a VM, and I reproduce it. And then I have to start looking at the operating system. What I did is I gave it a dedicated ZFS pool on a dedicated disk so that I keep it all separate from the operating system and sort of streamline the tracing I was doing, because ZFS gets a bit noisy if you start running dtrace on it. And I had a bit of suspicion that this has something to do with write caching, or something to do with the ZIL, which is the ZFS intent log, where transactions get queued up before they're written out. And those are used and replayed if we have to recover from a power failure. So what I do is I run a loop to reproduce this, and every time that I reboot the machine, I snapshot the disk, so I've got it in its state before it comes back up. And after I reproduce it, I can import that pool into a different VM and have a look at it and actually dump out the ZIL. And then we had I think by then, that was a very quick description, but by then other people had started to wake up on the East Coast. We got on a call, and I posted this data I collected, and I think it was Matt that very quickly came in and said, in this trace of records, I can see that we are doing 4 8K writes, then a truncate, and then a whole slew of writes after it. And wouldn't that explain why we have 32K of zeros at the start of the file?
That's got to be a great moment. Done. Yeah, that just feels like blood in the water at this point.
Yeah. So at that point, the hypothesis is that when we replay the ZIL after booting after a power cycle, a hard reboot, we're playing the transactions in the wrong order, or the transactions are in the ZIL in the wrong order. And at that point, you reach for dtrace and some speculative tracing and start watching. You got to use speculative tracing occasionally.
I don't know if you're just saying that for my benefit or not, but I just, let's just say that
that's true. I did.
A detractor once said that speculative tracing has never been used for anything, and I'd like to. Every time we use speculative tracing on a bug, I think of that particular detractor. So anyway, sorry. Go on, Andy.
I'll be entirely honest. It's maybe twice a year I use it, but when I use it, it's useful.
That's right. Yeah, exactly.
Yeah. So I start logging the calls into the functions that put entries into the ZIL and run the reproducer, and I can correlate a bug happening in conjunction with the entries being written correctly. So the reproducer that's in C, which is linked to from the Lumos ticket, is actually part of the Lumos ticket. That's presumably been pasted a few times in chat. It creates two random files, and then it copies one over the other, and it does that by opening the destination file with the truncate flag. So the very first write to that file should truncate it, and then you get all your data going. And it writes the data in 8K chunks. And I can see that we end up with this corruption, but all of the entries went into the ZIL or were queued into the ZIL log in the correct order, but they ended up on disk in the wrong order. And that was interesting. It shouldn't happen.
That's an important detail.
And there's a lot of dtrace involved here, but at the end, I realize that some of the write transactions are being committed to the ZIL as if they'd been synchronous writes to the file. And when you commit the ZIL to disk, you commit all the synchronous writes first, and then you do all of the asynchronous writes afterwards. And that explains why they're being reordered. But the question was, why are these writes going in as synchronous? They weren't synchronous writes, but they were put into the ZIL as if they had been.
Right. And
this comes back to an optimization that was put into Solaris in 2007.
Yeah.
When some were bringing
July 2007, exactly. I know. Alan and I both stared at this. Yeah, it is July of 2007 is when this thing comes in. July 24th, 2007.
Yeah, so this is when Sun were bringing up their new cool thread servers, the T1, the Spark T1, which were low power chips that had a lot of threads. So I think they had up to 8 cores, but each core could have 6 threads or something like that. That's something like 32 threads plus those early cool threads. They weren't particularly fast. They had lots of limitations, like 1 FPU for every core, that sort of thing.
Yeah, that a very serious limitation it would turn out.
Well, I mean, come on, who actually does floating point operations? Oh,
I mean,
okay.
Everyone all the time.
Everyone all the time.
Accident, right?
Okay, anyway.
Yeah, and at the time I was consulting for someone that was filling data centers with Sunblade 6000s and T6340 servers, and I had a lot of work parallelizing things, basically trying to. But yeah, Sun were doing this, and they were running. I'm reconstructing from what I can read in the Open Solaris book, which is the public information we've got. But it looks like they were running a whole load of benchmarks for different workloads, and they realized that when they did a workload that was supposed to simulate a busy mail server, which is lots of async writes and the odd fsync, there was an extremely hot lock in the ZIL code that was causing fsync to be slower than it should be.
This was coming out of the Niagara work. So I actually that's interesting. I thought this was coming out of the supporting ZFS in the field, but that's actually interesting that it was coming out of more of a synthetic benchmark.
Yeah, I mean, the ticket is all the information I've got, and it talks about some evaluation that was done, but I don't have the data. So
yeah, interesting.
But they were seeing slow fsyncs and a very, very hot lock. And their solution appears to have been, when a thread initiates an fsync, let's log the next 4 writes that thread does into the ZIL as if they'd been synchronous. And it takes a lot less work to insert it as if it was a synchronous write than if it was asynchronous, because a synchronous write just goes into the global transaction group synchronous list, as opposed to having to find the object, find the right list, chuck it on the end. That's what I think is going on.
Yeah, interesting.
I don't know why. I don't know why it's 4, but if you write your data in 8K chunks, 4 is going to explain 32K very nicely.
I appreciate, Andy, that you're describing this in the most generous fashion. And even as you do so, you're like, that doesn't sound right. That sounds fishy.
Whenever there's something like this, where you have this 32K, where could this possibly be coming from? And then you discover it's like, oh, it's 4 times 8K. 4. It's like, there's your answer, fishbowl. But that is, I mean, I don't know, Adam, does that, I often think of that where they have determined that that Homer is Mr. Sparkle and why that has happened.
Yes. Yeah, but even Andy, as you're saying it, like, hey, this really complex, primitive around synchronous semantics across which people reason, a barrier across which people reason. What if we just like, I don't know, like we're loosey-goosey about that? What if we just do that instead?
Loosey-goosey though, in kind of a strange way. You know what I mean? Like it feels, doesn't it kind of has like a feel of like, no, like I'm making this thing synchronous. Like making something synchronous is always like, I don't know, always feels better to be synchronous.
Right. Isn't that better?
Feels better.
Of course, if your system doesn't fail, it's fine because the data goes to disk in the right order and the stuff in the ZIL is never used.
Yeah, exactly. If this is a fail, why do you have the ZIL at all? I mean, it's
yeah, shut up, nerd. Right.
Yeah, and the only thing we have in the issue is something like, as was suggested in the evaluation, I'm going to hack up this suggestion. I saw some very positive results. And indeed, they did get fsync down significantly. But of course, unsafe at any speed from what they'd done.
As a sort of callback, part of the problem here was that we were f-syncing. We had crossed the barrier into too many f-syncs, and that put us into this window that would trigger this bug.
Right.
Like we had talked before about.
F-syncs followed very quickly by a lot of writes, yeah.
And Matt Ahrens, do you now do you recall anything? I mean, this is now truly, I mean, obviously 18 years ago. Did this issue ring any bells for you? I mean, is this or maybe more recently, because the OpenZ, I mean, this had been removed from OpenZFS, but honestly, not very long ago. So this is like
and kind of subtly, I like in the OpenZFS repo, it was sort of a, oh, by the way, we're going to remove this thing that might cause data corruption. But like, I was sort of expected data corruption to be like the above the fold. Not paragraph 8 subsection 3.
I think it was actually first. I think it was first removed because they were having trouble with the TSD, the Fed-specific data implementation on Linux or FreeBSD, whichever one they were bringing in. I think it was removed, then it was put back because it had a performance effect, and then it was finally taken out in 2023 with comments that said, we need to guarantee the order of rights.
Yeah, I think the original bug I went back and looked at. I mean, I don't remember this particular, where the original change that introduced this bug in Solaris back in 2007. I don't remember this particular change, but I definitely remember that era of like, ZFS is slower than other things, and we need to run lots of benchmarks, and we need to like make lots of like heuristic tweaks. And for sure at the time, I remember being like, like holding my breath for something to go wrong with messing with the inner workings of this sensitive, the ZIL is very sensitive, both to performance and correctness. And it's not like the easiest to understand subsystem.
Yeah. Yes.
So I love this description of this very politic description of your esteemed colleagues all volunteering to assist with performance work.
Yes.
Leaving you to worry about the correctness work.
That's right.
Yeah, that's kind of what it felt like at the time.
My job is to make the system faster. Your job. Yes.
Yeah, and I mean the bug report from back then, it has a lot of documentation about how they made the system faster. Right? The block is not as contended. The benchmark goes faster, which is great.
Yes.
But yeah, I mean that we were trying to get ZFS like to be more widely accepted. Performance is a big part of that when you're competing with like much simpler systems like UFS, as well as Linux file systems like ext. So it made sense to do this work, but I think it was known to be scary, and it just took like a couple of decades for us to figure out why.
And then in terms of when this work, I mean, because as you said, it was removed in OpenCFS, like 2 years ago. It feels like that might have been though as part of other work where someone realized like, oh, and also like I think this might have possibility for data corruption, or do you know, or was there a similar experience where this was actually debugged from first principles?
I don't know. I mean, the person who fixed that, Alexander, he didn't say in his bug report, like if they had customers that hid this or whatever. It kind of seems like he noticed a bunch of code that wasn't needed and then like kept digging around and then was like, huh, that's weird. Huh, that's weird too. Gee, this is really not great. And, fixed all that stuff, which is wonderful.
Yeah.
But yeah, like he totally buried the lead with like, you're like 5 paragraphs in. He was like, yeah, we cannot randomly jump between sync and async unless we want data corruption due to write reordering. Yeah, that is true. But I thought that the analysis that was it Andy did was great, and the write-up in the bug report, the Lumos bug report that you did, Andy, was really wonderful and evocative, and kind of told the whole story of where the bug came from and how it shows up. So I really appreciated that.
Well, and then Andy,
and one really nice.
Yeah, go ahead.
So one really nice thing that the developer did for us, whoever integrated this, they made it tunable. That number 4 was not fixed; it was in a global variable.
Yes.
And I assume, I got to assume. I assume they did the number 4 was arrived at by playing with it a bit.
Yeah, for sure. 100%. He tried a bunch of values to see what would perform best on that benchmark on that hardware 20 years ago, and that was the best value. And nobody ever looked at it since.
Oh my God, I know.
And what? In defense of that, so obviously a problem, but
go on.
That, like,
wait, what else can you do?
Well, there are numbers like that persist, I think, in ZFS, like 200 metaslabs per disk, where you're 100%. Like, that sounds like it worked really well on Jeff Bonwick's desktop machine in 2002, running at 5,400 RPM or whatever. I mean, I don't know whether that number should be higher or lower, or whether 200 is like some universal constant, but like constants, happen.
Adam, I love your entree, like in defense of this, because actually I want to go after this other thing I actually right.
Let me sideswipe Jeff for no reason. Yes,
sideswipe Jeff, exactly. But yeah, I mean, you're right. I mean, ultimately, when you have these things, I mean, our objective is to make all these things auto tuning. You can't do that for everything, but this was also the tunable, I think, kind kind that this was that there were some heuristics here. This was not a and that number again comes from, as you say, 20-year-old machine, one that probably doesn't bear much resemblance in many ways to the machines we run today. So, but Andy, this is in many ways the best possible thing. The fact that it is tunable. One means we can very quickly, this one feels like we've got a lot more supporting evidence around than we did around the 32K tunable that Matt had found. Feels like this is a little more on more solid footing than RipGrep, but it similarly allows us to explore this by tuning this thing down to 0, and let's see what happens. I think that was your next move, right?
Yes, and one of our colleagues, Justin, had to set up in his lab, and I think overnight he did 120 boot loops or something with it set to various values, and could prove that when it was set to 0, the bug never manifested at all. So we're pretty confident by then. That is not a complete fix, because there are other ordering problems in the ZIL, but we weren't hitting them with the workload we were running. But they have now been fixed, but we didn't need to necessarily fix those to get the release out.
Yeah, and we from a strict because we were holding the release for this for obvious reasons, and I think we knew that we had a cordon around this thing, blood in the water. Felt like it's one of these things where we're just gonna know a lot more in a couple of hours. So let's see where we are. And I mean, I was definitely concerned that we're gonna know a lot more in a couple of hours, and what we're gonna have is a really dicey fix where we're going to have a fix that itself is not going to be low risk. I mean, this is always the concern you have with something like this, where we actually know what it is, but now we need to go do surgery on the ZIL and then ship it to customers. Like, what can go wrong? And I mean, that's obviously we would do what we would have to do, but you just kind of hope, God, like, I don't know. We're just going to know more. So let's go know more. And then like, oh, sweet Jesus, there's a tunable we can set to 0 and just turn off this behavior you could not ask for a quicker resolution from that perspective, or a lower risk fix in particular. It felt like the risk of turning this to 0, there was some potential risk to performance, but not a regression. Not a regression. Have you, Adam, I'm sure you've turned Alan's perspective on a regression, on performance regressions. If you are transitioning the system from incorrect to correct, it's not a performance regression. It can't be. Because,
that's right. That seems right.
Because the system, as Alan has said many times over, if correctness is not a constraint, I can make this thing really, really fast.
Ergo, right?
Ergo, it is not a regression.
Right. Yeah, I like that logic.
I love that logic. I think whenever I mention this to Robert's like, well, I'm glad that you feel that way. It's like, by the way, the system is okay. That's great, but so I think that we
right now do Spectre and Meltdown.
Yeah, I know 100%. Exactly. No, it's like, it's like, I'm glad you feel that way. Customers may not see it the same way, but obviously performance is very important as well. But it does give you from a release perspective, it's like, no, we're going to set this tunable to 0. And now we've got a lot of confidence in actually shipping this thing out. But Andy, that's not like tuning it to 0 is not the fix that we actually want. We, I think, want to eliminate this entirely, or that's the fix you ended up doing. You then have further analysis because, okay, there is a performance issue here. And so let's go understand that. And then could you describe some of the follow-up work you did to actually look at the performance of this thing? And actually going back to some of this, like, all right, let's go back to this original file bench profile and let's see how this thing actually does.
Yeah, so we obviously wanted to fix it properly. So I went through and wrote up a fix and went through all of the ZIL logic and tried to fix all of the things I thought were problems. And then I went and found the same commit in OpenZFS. And it was pretty much the same. So they'd fixed the same things as we had.
Yeah.
And a further optimization around the ZFS volumes, where we used to do a cat ZIL transactions per object. And of course, there's only one object in a ZFS volume. So you can actually get a bit more speed there if you just treat everything as synchronous when it goes into the ZIL. So I pulled that in as well.
Oh, interesting. Yeah.
And got that up for review in Upstream and Lumos. And then I went and found File Bench and managed to get it to compile and managed to get it to disable ASLR and all the other things you need to do. And ran some benchmarks on old and new. I was actually on a Gimlet I went for, just because there was one on the bench.
Yeah.
And I've got to find the right word that isn't degradation, but the difference I saw
was
no more than sort of 2% change in F-Sync performance. So
F-Sync performance on this benchmark that is designed, or this benchmark which exhibited this problem. So
and it's actually a benchmark that's pretty close to Crucible Repair. It's a lot of async writes and a lot of F-Syncs scattered in the mix. I didn't spend the time to actually do one that looks more like Crucible, but we could do that. But at this point, we know it's not a massive blow to performance, and it is now correct, and it wasn't before. So that is the route we're taking. But I think we can do some further work in the future on this lock that is highly contented.
Yes. Yeah.
But we'll do it properly.
We'll do it properly. Yeah. Yeah. I think that there was some other kind of approaches that we want to go take. And I think also, I mean, this is from the performance of our system. This is a Crucible repair operation. Mm-hmm. That operation is itself asynchronous, right? I mean, it's like if the performance were pathological on that could actually be that you could have ways that would degrade some performance. But this is a code path that very much needs to be correct. All of Crucible needs to be correct, but this one especially so. And this is not necessarily. This is not. There are other paths in Crucible that are the hot paths for performance.
Yeah, and this isn't one of them.
This is not one of them. I mean, is that fair to say, On?
Yeah. Yep.
This ended up being we went from Friday feeling. I don't know. I mean, I guess you felt kind of despairing. I felt like excited that we had this thing actually reproducible. And said, we're going to get this. It may take us weeks, but we'll get this thing. Sort of at that point.
Yep.
But I mean, as we've seen so many times before, and as we saw, ironically, on the bug that was happening kind of concurrently with the first round of this, that we had Dave and Co on talking about, there was a baton being passed here as people are trying to, obviously Justin and Matt, but then also James, you being able to reproduce it simply, Dan being able to reproduce it even more simply in C, kind of setting it up for Andy to really be able to, again, put a cordon around it and really cinch it tight. Was just, it was a lot of fun to see.
It's a lot of fun now looking back. Yeah.
It is. I mean, on the one hand, it's like, God, it is great content. It is such great content. But on the other, it's like, maybe we don't need this much. We don't need to do that. We don't need, hey, gods, we don't need any, I don't know.
Some content, but maybe, yeah.
Yeah, maybe we don't. We're okay on this, actually. We've kind of people are like, Jesus Christ, another data corruption episode? How many of these things are you going to have? I mean, but it really was, it was terrific. And I think there are a bunch of, I feel, lessons here. With one of them, Matt, just in terms of your half measure, that I think was important. Being able to, when you see a pathology like this, instead of closing your eyes and pretending that it didn't happen, which first of all, you can want to do. That's okay to want that. It's just that what you actually need to go do is really try to actually go hit the system harder where you think it might be more vulnerable.
And if you don't, in the beginning, we didn't know what it was that would be hitting it harder. So what do we need to do to get that information? Okay, we can add more logging here. We can put some debug data in here. If you don't know what it is to do to reproduce it, then go do what you need to do to get the information that will help you,
Right, exactly. To actually go to, and the information, the tooling that you need to actually get this stuff nailed. But Matt Ahrens, you should know that the affidavit holds, you're and it continues to be very valuable to that. And I also very appreciative of having, even though we are, we've kind of got different ZFS implementations out there, very helpful to have, to be able to compare notes across those implementations for sure.
Yeah, sure thing. I found that email that I think you're referring to from October 2023, which was just a few days before the fix was integrated into OpenZFS. So I don't quite have that excuse for not, code reviewing and understanding all of the ZIL before I sent Adam the affidavit, but glad it was helpful.
Yeah, it remains helpful. It was extremely helpful because it was, again, allowed us to make this very important transition in the system that Matt described earlier. So it has been very helpful. And again, terrific work all around.
Truly a team effort. Everybody from all directions throwing in little pieces that move sort of the whole process along. It's a very, very important aspect of this. Data corruption needs to be shared suffering. It really is very important. And I also, when debugging problems like this, I think they're very parallelizable in the sense that people can try things out. I mean, when for example, when Dan was trying out writing this in C, it's that's fine. Go down that route. If it yields something, that's great. If it doesn't yield something, that's fine, because lots of other routes didn't yield anything. And then, oh, wow, it yields something. Great. Okay, that kind of lurches us in that direction. So, yeah.
Well, awesome. Thank you, everybody. Andy, thanks for your terrific analysis in the Illumos bug. We'll link in the show notes, but 17734 is the Illumos bug that goes into the actual details, and really terrific work on all of this. And thank you, everyone. Matt Ahrens, thank you again for the affidavit and for your all of your great help from afar. And now I really need to go figure out if I'm hallucinating this DMA issue from 20 plus years ago. That
Silicon Image.
Silicon Image.
It sounds very truthy.
It does sound truthy. It sounds truthy, which is what makes it so plausible that I have told myself some elaborate lie. Well, anyway, I'll go do my homework on that.
Someone said you mentioned it in a talk like years and years ago.
Oh, I for sure have mentioned it in talks like that. Sorry, if that's the standard for I definitely know I've done
You've
that.
incepted yourself.
Oh yeah, I mean for sure on that one. This is what has me concerned. It's an implanted memory because it's extreme. I mean, it's a great yarn. You know, it's like maybe the thing is I even remember whose office I was in when this thing got named. I mean, it's like if this thing's implanted, it's elaborate and it's really.
Do you really want to know?
No, you know what?
Maybe it's better if you don't.
You know, maybe I don't. Like, what? You know, who's to say?
Just let it be. Yeah,
let it be. It could have happened, and that's the point, really.
Yeah.
No, I definitely have told this one plenty. This true or not, this truthy story, I've told plenty.
It's a parable. It's got a whole lesson to it.
It's a parable. Awesome. Well, thank you very much, everyone. Thanks. I know what I will be giving thanks for at my Thanksgiving table. Correct data.
There we go.
Awesome. Thanks, everyone. See you next time.